So you should have your two colors that we'll use here momentarily. We don't need them like right this exact second, but I figured we just start by having them out. Okay, so actually the calculations went pretty good yesterday. You're gonna see we're gonna be putting this together where we look at the total mechanical energy. So being able to identify and solve for the individual variables is going to be huge. It's going to be a big part of how we end up this unit. So just realize what we just did is not going away. But what we're going to look at, and the one brain pop kind of showed this really well. It had like little diagrams at the top, and I had these bars that were kind of like going back and forth. Those are actually called energy diagrams or energy bars. And so these are going to show the amount of energy in an object. And so they can be vertical bars. The ones on that video were like showing horizontally, like filling with potential and then filling with kinetic and back and forth. But basically what it's doing is showing the total energy in a system or in a certain situation. And then from there, it's going to show how it goes back and forth, going from kinetic to potential and potential back to kinetic and back and forth, because that energy is never destroyed. It is never created. It is like, it's just fixed. And so then it just transfers back and forth between those two main forms, kinetic and potential. And so in an energy bar chart, a bar is constructed for each form of energy. And then the length of the bar is representing the amount of energy that's actually present. So how tall is the bar or how short is the bar matches the energy that it's meant to represent. And I'll show you what these look like. There's a lot of different forms. Once you realize like what the types of energy are, like it's pretty basic, self-explanatory to kind of interpret them. Right? And so obviously a longer bar is going to represent something that is showing more energy of that type. So maybe more kinetic or more GPE. And again, a lot of times we won't say gravitational potential energy, we'll just be talking potential energy. But understand that's the form that we mean. So here's what it might look like. So KE is kinetic, PE is potential, and then this TME is not a typo. It's not supposed to be time, and like we forgot the I. This T means total mechanical energy. Okay? And so you see for each stage, of this little like ramp or roller coaster system. So at A, it's all potential because you have all the height. Notice the yellow bar, the TME. That isn't changing. So in this system, from here to here is a set amount of energy that is available. And that is represented by the total. And that total is constant. The remaining bars that are there have to add up to reach the total, which only makes sense. If you have the total of something and it's made of two parts, those two parts have to combine to make the total. So you have no kinetic because it's not moving, but you have all potential because it's at the highest point. And so if you add this bar with this bar, you get the height of this bar. Now this one's a little easier to see. Here is B. So you have some vertical height. So you have quite a bit of potential energy, but it's also moving, so you have some kinetic. So you take this, add it to this, and it becomes the same height or size as this bar. Now we go to C. My height has gone down a little bit, so that means it has a direct impact on the potential energy. So my potential gets added to my motion or my kinetic, and it equals my total bar. Right? Now we are looking at D. At D, it looks like that is the reference point. Well, what is the height if you are at the reference point? What do you think? What do you think?
0.
Yeah, 0 height. Very good. So if it's 0 height, plug that into the equation. Mass times gravity times height. So it doesn't matter what the mass is. Gravity's 10. If you times it by 0, your potential energy is going to be 0. And the energy doesn't go away, so then that means it has all had to transfer into kinetic. Right? And then here we have just a little bit of height, so we've changed some of the kinetic into potential, but if we add these up, right, it equals our total. And really, this is, like, it's very logical. Like, if you look at this and understand what these types of energy are, it's pretty basic to see, okay, those have to combine to equal the total, right? And they always do. The thing with these, I think this is stationary. I can't see motion, but I can see the height, right, Brady? You can see the height. This is the highest. So at the highest point, it's going to be all potential. At the lowest point, it's going to be zero potential. So by default, it has to be all kinetic. So there's some things right off the get-go that you can interpret. Find the highest point, that's where you're going to have the most kinetic. Find the lowest point, that's where you're going to have the lowest or no potential. And then that means you have to, by default, have all kinetic at that point. Yeah.
Will the TME always be full?
Yes. Yeah. Yeah, because here's just kind of generically, like, it's like, here's the amount. And like, do we really even know what the amount is? Not in this example. Okay, but yeah, it'll always be full, just to make it kind of easier. So, yeah, good question. All right. So this can also be done using or showing with circles. So we can use the bar graphs, we can use circle graphs. It's still an energy diagram showing the amount of energy in an object, but it's using the circle represents the total. All right, so we're not going to have like 3 separate circles. We have one circle, and there's going to be, part of it will be representing kinetic, some of it will be potential, but the circle itself is representing the TME, or that total mechanical energy. And so it's also, obviously, they can be called pie charts, circle graphs, and they're constructed to show the percentage. And these work well, again, because kind of going along with what you said, Echo, 100% fills the circle. And so that represents the 100% of our total energy. Right? So kind of just in the nature of how they're naturally set up, it includes a total. And then you fill percentages to match the type of energy at that particular point in the system or the situation. Obviously, the greater the percentage of the circle that's filled in means the greater amount of energy for that specific type. So if it's mostly filled in for kinetic energy, then you know it has a lot of motion and it doesn't have a whole lot of height. If you see a whole lot of the potential energy color filled in for that circle graph, then you know that it has a lot of height and not as much motion. And really that's what this comes down to, is just understanding what those key things mean. All height means all potential. No height means no potential. And if you have no potential, then it has to be all kinetic. And if you have all potential, then it has to be no kinetic. Right? So basically they kind of work like in opposites. If you have all of one, you have none of the other, and vice versa. Okay, here's where your colors are going to come in. If you need to grab 2 colors, if you have pens, you can use them. If you need to grab colored pencils, you can grab 2. So here's my colors. They're going to be kind of like this pinkish red for potential energy, and then blue for kinetic energy. And so we have a roller coaster. So this is the system. This is the situation. So these circles are representing the total amount of energy at that point on the track, right? So the amount of energy, how it's distributed here, 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 and here. And again, looking at this, most of the time you can't see the motion, right? This is a stationary image. So I can't really say, oh, it's going to have all kinetic all the way up here. Well, I don't see that moving, but I can see the height. So if this is my reference point, I know, okay, this is the highest, then this, then it looks like this, and then this, right? And then finally the lowest look like they're going to be here at 2 and 5. Okay, so I can visually see height. So for me, that's where I like to start. It helps me kind of figure some things out. So we're going to watch this. Let's go. Give this a little launch. All right, so I'm going to go step by step. Well, actually, I'm going to play it through first. So watch as it's gaining height, meaning it's gaining potential energy. Now it's going down, so it's losing or transferring. Okay, and watch again. So as it height increases, my potential color will increase. As height decreases, my potential color will decrease and it will be replaced with kinetic. Okay, so watch again. Notice the total amount of energy is not changing throughout the whole system. It is just a matter of what percentages do you have. So we're going to look at step 1, and you have this, make sure, because sometimes you forget to do this, there is, in the bottom right hand corner of your notes on page 2, it has PE equals, put the color that you're using for potential energy right there. And then your KE equals, make sure you put the color that you're using. Okay, so at step number 1, you're going to color, let's say you used green for potential energy. You would color your circle all green, okay, because it's all potential, which matches because it's at the highest. You might also want to write in highest right here, just so like if you're looking at this later and you're like, why was that again? Step 1 is the highest. Okay, let's go to the next step. So we're going to change some of that potential into kinetic. And so this is just barely above what they're calling the reference point. So it's not quite at the lowest. And I know that because there's a slight sliver of potential energy. And just like Garrett said before, if there was no potential energy, it'd be because there's absolutely no height above the reference. It'd be like resting on it. But here it must just be barely above the reference point. So here you're going to have maybe just a line or a sliver of your potential color and then shade in the rest your kinetic. Now we're going to go to step 3. Okay, so we're just working our way up. So we've gained a little bit of height. It's like a nice healthy slice of the pie or the pizza. And that is for step 3. Still mostly motion, mostly kinetic energy, but we do have a little bit of height. But we're going to continue to gain more height as we move on. You guys ready for me to go to step 4? Okay, so now notice that step 4 is the second highest in my system. So it's going to have close to about 3/4 of potential because it's about 3/4 as high as at step 1. Now, does it have to be perfectly proportionate? Not really. Just know that it's going to be the one that has the second most potential energy color. So 1 will have the most, 4 will have the next, 6, 3, 2, and finally 5. So we have a lot of height, meaning we have a lot of potential energy. And think about the variables in the equation, mass times gravity times height. It's the only equation that deals with height. So if you're looking at height as giving you information, it's giving you information on the potential because that's the variable that's in that equation. All right, let's go to 5, which is an easy one. Now I know that this is at the reference point. It is at the very lowest of the entire system. It is basically like ground zero. Now, is it actually the ground? Not really. It's actually the very bottom of the track. So again, the reference point doesn't have to always just be the ground. And now we're going to gain a little bit of height. So you're going to have a little bit of your potential color is going to increase. And it's going to be really similar to the 3 was right here, so it's a little bit higher than 3. So maybe about 1/3 of its energy as potential at this point. These are not difficult. The hardest thing is to make sure you keep your color straight and you know what color you're looking at to represent each type of energy. But the logic of it is very straightforward. Do you guys have any questions on that part? Good. All right, so I'm gonna also, it might be helpful if you want to write it number 5, the lowest. And that helps you remember, okay, when it's the lowest, that's all kinetic because you have no height, meaning it would make your GPE 0. Okay? So at the highest and the lowest, you're going to have all of one and none of the other. And that's going to be important when we start doing some more calculations a little bit later. Okay, let's go. So you should have something kind of like this. At 2, mine's messed up just a little bit. It should have the sliver of potential. And it doesn't matter if this blue was down here or if this red was down here, as long as the percentages on that circle are the same, it doesn't matter. I think mine are, like this one I think is reversed from what was on yours, but again, it doesn't matter. It just goes off the percentage. So it doesn't matter if you would put it where the slice is off to the side or at the top or at the bottom. That has no effect on it. Make sense? Good? You scare me when you're so quiet. We'll blame Brookston since he's not here. He must be the noisy one. Okay, so let's take a look at this. Excuse me. So we're going to shade in the bar graphs. So instead of using circles, now we're going to use these bars. What is a little different on this one? It doesn't have a bar for the total mechanical. So Echo, going back to what you commented on, the height of the bar is the total amount of energy that could possibly be present. So could there be a third bar on all of these? Absolutely. Right? Ooh, it's a little short. My pen's not the greatest at the moment. Try again. So there could have been a third bar. Supposed to be the same height. Okay, you could have had a third bar, and this could have been our TME, right? But since there's not, we know that kind of by default, the height of the bar is representing like the total height of the system that would be possible to be there. Right, so using your potential energy and your kinetic energy colors, we're going to fill these in. So again, for me, the easiest thing to do is to pick the highest point and realize that that is going to be representing probably the majority of potential energy, right? So I picked the highest point here, so that means that this bar is going to be, it's not quite at the very top, so I mean, I'm assuming we're going to fill it in about that high, and then you'd have to fill in the rest for kinetic. So mine kind of goes like this. Notice how I have a little bit of a gap, and then the rest of that is filled in with kinetic. But these two, if they were stacked on top of each other, should totally fill in to the full height of the bar. And then this is the second one, the second highest, so I'm going to make this my second tallest potential bar. And then whatever I don't use as potential, I need to fill in with kinetic and make sure that those, if they were stacked on top of each other, those two colors would totally fill the bar. And then I go to my third highest, and so notice, like, you know, you're just making the bar a little bit shorter and a little bit shorter as you lose height as you go down those hills. But really, without being able to identify the height easily, these could get a little tricky. But because height directly relates to the potential energy, pick the highest and I work my way down, or pick the lowest and work your way to the highest. But height is really going to be the one thing that's kind of like your go-to, like always make sure that you're looking at that to help you figure out how filled in that bar or that circle is going to be. Any questions on that? Usually this is pretty good. You guys aren't giving me a whole lot of feedback. Yes? No. Thank you. Okay. Okay. So the law of conservation of energy. This has been mentioned in a couple of the videos. We talked about the law of conservation of mass. Hold on. Hello? I do. Okay. Just send her straight there. Okay, I will do that. Bye. Maddie, you need to go to room 237 so it's makeup testing. So you'll need to. Good luck. You thought you could miss and like just be exempt, didn't you? Yeah. All right. Okay, so energy can never be created or destroyed. So this means energy is never technically lost. It's only going to be transformed or go back and forth between multiple different forms. And the Bill Nye, I mean, almost all the videos we've talked about or watched have talked about this idea. Okay, so honestly, the amount of energy in the universe is the exact same amount today as it was 4.6 billion years ago when the Earth was formed, right? So if you think about it, it's kind of a very constant, very lasting. Is it amount that we calculate? Not necessarily, but energy can't be created and it cannot be destroyed. And so it's a good thing, I guess, that it can be transferred into different forms. Sometimes it seems like some of it's lost, like because some will transfer because of friction into heat. And so this is something that we talked about back with our states of matter. But technically, all energy in a system is accounted for. A lot of times we say it seems like some of it was lost, but because friction and it's kind of wasted, but it's still there. It's transferred into thermal, transfers into, you hear some of that sound. So the friction can transfer it into even some of the other forms. So we call the total energy in a situation the total mechanical energy, or TME, and it's the sum of your kinetic and your potential. And I believe this is one of your vocab terms. It's kind of set up like this. It's kind of a weird vocab term, but people were struggling with it a few years ago, so I was like, okay, we're just going to make this one of your vocab so it's something that you kind of keep getting put in your face every day. And so we're going to be looking at the total mechanical energy, or the TME. And so one type of common transformation that we aren't always, it's not like we're usually trying to create this. Usually a lot of times we're trying to reduce friction, but if we could get rid of friction altogether, then you know, the energy transfer would be a little bit more straightforward, like it'd be a little bit more equal, where it goes from one all to another. When we go from one, usually some gets lost or transferred into friction, and that is not usually a usable form of energy. So it still transfers to another form, but it's just not usually as productive or useful. And because of that, we call it like a latent or a wasted energy. But it's still following our law of conservation of energy because it's not disappearing. Okay? And so some kinetic energy is always, if there's motion, you're going to have friction. And if you have friction, some of that is going to transfer into thermal energy. Just like rubbing your hands together, you have that, you feel that heat. All right. So, you know, if the purpose is to have a fan, well, a fan will get hot, like the motor of the fan and the movement of the fan will cause the moving parts to kind of warm up. Well, the purpose of a fan is not to create heat. It's usually to help spread the heat and move it away, right? And so it's not like you're trying to create that thermal energy, but because you have those moving parts, there's friction, and that friction will cause some heat, right? So a lot of times, total mechanical energy, we have to account for the friction that is created in that movement. But here you can see the total, the TME is now green. We have kinetic energy, and as this little cart is moving, again, as I see it going down, I lose potential. As I'm going up, I gain potential. And again, when I'm saying lose, we're not really saying like it's going away. We're saying transfer. So it's really transferring into kinetic or transferring back into potential. But you can see the adjustment of the bar. So at the highest, it's all potential. As it's going down, you're gaining kinetic and changing from potential. Now as you start to go back up again, right, you see those transfers back and forth. Okay. So we already kind of talked about this. The side effect is heat or thermal energy as things move past each other. And so that good old timeless example of rubbing your hands, right? You can hear, which is sound energy, and you can feel the heat that is created or transferred as those objects, your two hands, rub past each other, right? And so that thermal energy is a major way that some of the potential and kinetic energies get some of their energy transferred into, or what they get transferred into. So in a perfect physics world, a person would be able to jump from a diving board, hit the water with the exact same amount of energy as they jumped, or as they started before they jumped. So if we have all potential, we have no kinetic because he's not moving, but he's at the highest, so it's all potential. And then you see it gradually transfer as he goes down. He's losing height, so it means his potential is going lower, and then the kinetic has to take up the difference. Here, about halfway, as he is getting lower and closer to the water, which is the reference point, now he has more kinetic and he has less potential because he's getting closer and closer, lowering his height. And now he has all kinetic and no potential at the reference point. But we know that that's not exactly what happens because you do have the transfer, but there's some other things that happen. There's also air resistance, which is a friction. And so a little bit of that kinetic and potential energy is going to transfer into that friction. Also, when the diver hits the water, there is friction. And so some of the energy is transferred into as his body slides through the water. And also the sound, the splash sound that he makes. So a lot of times in these problems, we're going to try to ignore friction just because this is an introduction to all this. And so it makes it a little bit more complicated to have to try to figure out the friction that's involved with it too. But just realize that it is something that is definitely a part of this. Okay? It's not going to go away. So in the real world, we typically would have the friction involved. So we're going to stop there and end today with